closed end tubes, and we're looking at standing waves. This is with one end closed and one end open. So what happens when we, say, put an end cap on one of the tubes that we used in our lab on Wednesday? Turns out the pitch drops by an octave, which, if you remember our lesson on intervals, that means that the frequency was halved from what it was previously. In the case of the two tubes that were C, we took the short one, which resonated at 512 hertz, and put an end cap on it. It now resonates at 256 hertz. So if my frequency is halved, my wave speed has not changed because the medium hasn't changed. Therefore, my wavelength has doubled. But the length of the tube did not change at all. So that's going to lead us to a different looking picture. Now, only a quarter of the wavelength fits in the tube instead of half. So it looks something like this. Again, remember that open end of the tube has to be an antinode. Okay, so to get to the second and third harmonics, let's think about this. If the open end has to be an antinode, all right, a closed end is a node, and that's always going to be the case. So if the closed end has to be a node, all right, let's see. Let's figure this out. Well, it turns out, all right, that in order to get a node in the middle and then a node at the end, I've actually gone from 1/4 of a wavelength to 3/4 of a wavelength. If I wanted half a wavelength in there, I'd end up with either two nodes, and I'd have to have both ends closed, which doesn't work, or I'd have to have both ends open. So it works out that for a tube that is closed on one end, there are no even-numbered harmonics. All right, so what does that make the equation? All right, so it's very similar to an open-ended tube equation, but here n is only going to be able to be an odd integer. All right, and instead of doubling the length, I take 4 times the length. Okay.